Hello, this is the application of computational fluid dynamics course. My name is Isaac Perez Raya, and this course is offered by Rochester Institute of Technology in the Kate Gleason College of Engineering. The tutorial is named Simulating a 2D Heated Plate. Let's read. This tutorial provides a comprehensive review of the process to conduct a 2D simulation of heat transfer in a solid plate. Figure 1 shows the solid plate, the heated plate, the boundary conditions, and the dimensions A and B. The heated plate considers a linear increase in temperature given by this function. That means that at y equals to 0, the temperature of the heated plate is 0, and that at y equals to A, the temperature is equal to A. Now, the horizontal boundaries are insulated. Insulated means that the heat flux along the normal surface is 0. If the heat flux along the normal surface is 0, then it means that the temperature gradient along the normal direction is 0. This is also known as symmetry boundary conditions. The dimensions are A equal to 1 meter and B equals to infinite. So we are dealing here is with an infinite plate. Don't worry about this. I will show you how to model this condition. Now, these are our objectives. Number 1, simulate heat transfer in a 2D infinite plate using the software ANSYS-Fluent. Number 2, identify the heat transfer distribution of the solid plate. The solid plate is in contact with a heated plate that has a temperature that changes along the y direction. And number 3, verify the simulation with a theoretical solution. Now, these are our assumptions. There are no variations of temperature with time. The plate is also homogeneous with constant properties. The material is solid and is not melting. That means that there is no velocity within the solid. The plate is static and there is no internal heat generation. We will assume that the temperature distribution on the plate is constant. Again, on the heated plate is constant and changing only along the y direction. Also, we are interested on finding the temperature distribution on the solid plate only. We are not interested on finding the temperature distribution on the heated plate. Therefore, the simulation does not need to include the heated plate. So only in this region. It is a 2D simulation and the solid plate has no thickness. This problem has a theoretical solution. Now, these are the methods. Number 1, review and understand ANSYS-Fluent literature for the simulation of heat transfer in solids. Number 2, identify the governing equations and boundary conditions. And number 3, perform the simulation using numerical software ANSYS-Fluent. Number 4, post-processing of the simulation results. Okay, let's start with number 1. Review and understand ANSYS-Fluent literature for the simulation of heat transfer in solids. So step 1, open ANSYS-Fluent Theory Guide 15.pdf. I uploaded this manual into my courses. This manual shows the different models available in ANSYS-Fluent. Now go to chapter 5. This chapter shows the different models related to heat transfer. In chapter 5, now go to section 5.2.1.10 and you will see energy equation in solid regions. This section shows the equations that the software ANSYS-Fluent solves when simulating heat transfer of a solid. This equation is the heart of our simulation. We will use ANSYS-Fluent to solve this equation together with the specified boundary conditions. The equations that the software ANSYS-Fluent solves when simulating heat transfer of a solid is given by, so we have this equation, right? Where T is the time, rho is the density, B is the velocity, H is the enthalpy, K is the thermal conductivity, T is the temperature, and SH is the volumetric heat source. And by definition, the H is equal to the sensible enthalpy and is equal to the integral from Tref, from a reference temperature to the temperature value of Cp dt. Okay, now let's review our assumptions. Remember, we assume 2D domain, we assume constant properties, no variations of the temperature with time, that the material is solid and it is not melting, the velocity of the solid is 0, and no internal heat generation. Under these assumptions, this equation at the top becomes this equation at the bottom. So now, in your report, please make sure that you derive this equation. So go from here to here. Equation 3, or this equation, is the simplified heart of our simulation. It looks less scary than equation 1. Now, let's do to the second step. Identify governing equations and boundary conditions. The governing equation is given by equation 3. The boundary conditions are given by the following equations. Okay, at x equals to 0, the temperature changes as a function of y, that is the temperature of the plate. At x equal to b, we know that it is an infinite plate. So how to model this condition? So at x equal to b, we don't know what's going on, but we will figure out a way to do it. We only know that is an infinite location. At y equals to 0, the plate is insulated. So at y equals to 0, we are in this boundary. You see? The plate is insulation. Now, let's go to the next one. At y equals to a, the plate is insulated too. Again, insulation means that the temperature gradient is 0. Now, let's deal with the infinite plate. The infinite plate is modeled by placing the boundary far away from the bottom boundary. This is how we will handle that condition. Therefore, it doesn't matter which temperature we specify in this boundary. However, the boundary should be placed far from the bottom boundary, right? So at x equals to b meters, we have any temperature, and there is a typo in there. Sorry about that. We have any temperature, and we will make b equals to 5. So 5 meters I hope these 5 meters are long enough so that the location of this boundary does not really affect the temperature distribution near the heated plate. And by doing that, we are simulating this infinite length plate. Okay, so now let's work on it and do the simulation. And I will do that in my next video.